Hello, everybody.
Hello, everyone.
So welcome. We are going to wait a few minutes, couple of minutes, so more people can join. So throughout the webinar, don't hesitate to ask questions in the Q&A tab, and we'll either answer them as we go or at the end after the demo. I think let's wait one more minute, Vincent, and then we can start.
Sure.
Normally, you should all have access to subtitles too in your language if needed. The presentation will be in English.
Are we ready to start?
All right, yeah, let's go.
Let's do it. Welcome, everyone. My name is Vincent. Welcome to this webinar, a concept exploration for structural parts, a live introduction to cognitive design. So today in the call, I have Henri de Charnassé, who's the CTO. If you want to introduce yourself.
Yeah, hi everybody. I'm the CTO and co-founder of CDS, and I take care of the R&D and development part of the company.
And I'm Vincent. I'm COO, and I look after partnerships. Welcome, everyone. So the idea of today is to give you an introduction about CDS, Cognitive Design System, also talk about the core technologies that we have developed, such as implicit modeling and parametric design, and also go through some introduction of the platform called Cognitive Design. We'll go through different demos, do a deep dives of different use cases, and we'll conclude with Q&A. As mentioned, feel free to interact with us in the chat box. You can ask questions and we'll answer them either during the webinar or at the end. So just to begin, a quick introduction about CDS. So we are a French company based in Toulouse. We come from engineering and we provide our clients with software. We cover three main industries such as aerospace, defense, and automotive, mostly industrial players. And most of our clients are actually OEMs, so original equipment manufacturer in various domains. We have a global coverage through our network of resellers. So we are present in Asia, in EMEA, and NAM. And today we are a bit more than 20 people. Most of the team is based out of Toulouse, but we have people spread out around the world. And we have I would say, a deep experience of engineering design. So this is in short CDS. Now let's dive into the platform and our product, Cognitive Design. So the idea behind this platform is really to transform engineering to a cognitive creation. And we do that by accelerating the design engineering. To do so, we use and leverage AI and automatization. So the idea is to really shrinken and make engineers more effective using new generation tools that will help them to engineer next generation design. When we look at the traditional engineering process, we go from manual concept creations to different stages such as simulation, manufacturability, business feasibility, to have actually an end product that is manufacturable. And we find that very often this process can be iterative, where simulation goes back to CAD, to manufacturability study, and so forth and so on. And when you work with large companies, typically you have also technological like silos, and this makes the process not so agile. So the idea behind CDS is to really shrinken this product development, make it a lot more efficient, introducing automatization and different sets of algorithms that will help you design and explore design more effectively. So instead of doing that manually, we have a different set of optimizations tools that will help explore variants of design. And so you can make trade-off and find the best solution for your needs. So the idea is to reduce the product development cycle for up to 5 times compared to conventional like CAD design tools. And a lot of it has to do with the automatization that will go through that together. And also the different, I would say, tools that we have developed that we'll see into the demo, such as generative design, parametric design, optimizations, and also workflows that helps us create streams of design changes that can be replayed anytime. And on top of that, we have developed AI capabilities to automate even more these design phases. Let's dive into our key technological enablers with Henri.
Yes, so there are 3 pillars that support the platform. The first one being implicit modeling. So we have our own geometrical engine that was developed at CDS. That is a hybrid modeling engine combining the power of implicit with the reliability of CAD and meshes. So a lot of our operations are based on this, and this allows to have a really robust automation. Second one is parametric design. So you will see after, because it's a computational design platform with blocks that you connect, every workflow that you will make will be reusable. So it's really interesting. If you want to make a variation of a part, you don't have to redo everything from scratch. You can just change some parameters, redo it again. And it's also usable for other parts too. Like if you have similar use cases, you can just keep your workflows that you took in one project, reuse it after. So really handy. And the third one is the AI-driven analytics. So we have a lot of tools to do analysis. So you can characterize your design, calculate some KPIs to have the performance, the cost, carbon footprint, and the manufacturability. So every design that you will make, you will see after, will have a scorecard with all of these scores. And yeah, quick reminder on implicit modeling for those who don't know. So it's fairly, I would say, new technology. It was mostly used before, like 10 or 15 years ago in the animation industry. Now it came to the engineering industry. So it's usually BREPs, so boundary representation. So that's all of your CAD formats, like CAD part, .prt, .step. These are represented by the outer surfaces. So you track the surfaces, and when you do modification, you recalculate the intersection between surfaces. On the contrary, implicit modeling, it's the full volume that you track. So it allows the operation to be really robust. You won't really have any problems. For example, if you put a fillet, if it goes a bit too far, usually you would have some topology errors on CAD. But here we don't have them. So it's really good for automation. Yeah, so you can see the difference between like CAD design and parametric design. So even if CAD is kind of parametric, right? It's mostly for your part that you are making. So you don't have the whole intent that's parametric. On the contrary, on cognitive design, if you do, let's say, a workflow to optimize a part for a jet engine, then you can use it for other jet engines. You don't have to redo everything again from scratch, which is really interesting and a huge time saver.
Should we dive into seeing that
Yeah.
in real?
Yeah, sure. I will share my screen. Okay. All right. So yeah, before we deep dive into the whole demo, I will just show you how the platform operates. It's really simple, actually. So you have these blocks that you can connect together like this. And you put your requirements to do some operations. So here, for example, let me just import a simple bracket, like this one. I can just click compute here, and I can have a visualization of my bracket. So here you can see it's a CAD model. And for example, if I want to do some operations on it, for example, let's say I want to make it lighter for additive manufacturing and add lattices inside, I can just use here that lightweighting block. So I connect my part to the lightweighting block, I connect it to the compute block, and then I can just run the calculation. And here, these are the requirements that I can put. So by default, for example, it's using surface lattices. So you will see them here, what is calculated. And I have a thickness of 2 millimeters. The shell also has a thickness of 2 millimeters. Here, you can see if I cut the part, you can see these lattices inside. And I can just like change these requirements to have a different variation. So for example, if I wanted a different pattern of lattices, I can just switch it here, then recompute. And then my geometry will update, and I will have the new model with the other lattices inside. So fairly easy, and a lot of the operations that we have are kind of monolithic like this. So you have a single block that you can use and put all of your requirements inside in order to optimize your part. So here you see you have a different pattern. I can also, for example, make the shell a little bit bigger. So the shell will be that thickness here. I can also put, for example, some radius between the lattices and the shell. And just run it again. Fairly easy. And if I have a different part, I can just use that same workflow. I just need to change the input here and run the calculation again. So quite straightforward. Here you can see my shell here is a little bit bigger, and I have a radius here. This is thanks to implicit modeling, actually, because it's fairly hard to do in CAD, right? And at the intersection of the lattices and the shell here, you can see that we can put some radius automatically, which is really nice if you are into 3D printing, because it removes the risk of having cracks, for example. Yeah, so quick intro on cognitive design. I will let Vincent finish the presentation, and then we can go back to show you like more advanced workflows.
Sure, let's do that. All right, back to the presentation. So CDS and cognitive design is not just a software for lattices or implicit modeling. It goes even more than that. So what we will see together is the generative design capabilities. And we often use that to perform design generation, where we'll create different variants so we can compare them. So instead of generating or drawing manually one design, we'll maybe generate 50 and see those trade-offs. And so to compare that, we need a tool. It's something that we call design exploration, which is a multidisciplinary exploration that helps us to compare design between them. For example, is this one heavier than this one? Is this one more stiff in terms of stress? Is this one more manufacturable? Is this one more costly? You see all those KPIs as part of the design exploration, which helps you track the differences and the variant. And at the end, the workflow automation helps you triggers those combination of generative design exploration to go even faster. So really, the idea is to capture the design intent, as Henri mentioned, to really automate what you want to do when you optimize a design for different purposes. What we have seen together is capabilities such as lightweighting. For example, if you focus on additive manufacturing, you can easily put lattice or TPMS, but you have all those other strategies such as topology optimization. We have also developed our own algorithms such as topology weaving that helps you to lighten a part. But we also have different capabilities that are more on the manufacturing aspect. So the second one is called manufacturing-driven design. It's a block that helps you to improve your path for different manufacturing methods. We cover 5 different methods today, so additive manufacturing, machining, die casting, forging, and injection molding. And the software will help you implement design for manufacturing rules automatically. And we will see that together in the demo. And last but not least, we have also a meshless solver. So we perform simulation-driven design that combines with implicit design. So the beauty of that is that you can use the result of a traditional FE analysis or a solver to drive the modification of your parts. Typically, in this example, you can thicken locally the part based on the stress that you have obtained. And today we cover 3 types of simulation: thermal, mechanical, obviously, and thermomechanical, which is the combination of the two. We can also accept third-party simulation data. So if you use software such as ANSYS, Abacus, or others, you can import the results back into a software to drive the geometry changes. Now, this is just a quick video. We will see that together. As I mentioned, we can use generative design to create a lot of different combinations, coupled with workflow to generate even more variants and structure, and compare them, apply filter, focus on parts that are above a certain manufacturability score, or compare a certain a KPI such as the cost, the displacements, the weights, and so on. And we'll see how we use that to perform engineering project. Typically, when you want to do a new concept, sometimes you're not sure about the material, so you can play on different materials, on different manufacturing methods, for example, 3D printing versus conventional manufacturing, and so forth and so on. I'll give it back to you, Henri, for the live demo.
Yes. All right. Okay. So let's go back to cognitive design. So I will show you how it typically goes if you want to optimize parts, especially to do topology optimization. So of course you can start from scratch and put the blocks yourself, but I would say 80% of our users just use the templates that we have here. So for example, we have this really handy one, which is called single body topology optimization. And you have everything that is already connected to do both topology optimization, manufacturing-driven design, and also track everything with the design exploration tool. So if we fly over the workflow very quick, here you have all the preparation step where you can import your parts, select your material here, aluminum. Here you have your surface selection blocks in order to put some load cases on your part. So we will see just after that we are able to fix some zones, apply some forces on other zones, etc., etc. Here you have all the simulation setup that we don't really have to touch. It's already set, but we can change it, of course. Here we have the topology optimization, where we will be able to choose a target, for example, reduce 50% of weight. After this, we will have the manufacturing-driven design, where we adapt the result for the manufacturing process that we want to use. And at the end, we have some validation step where you can recalculate the performance of the part using simulation and calculate other KPIs such as cost, manufacturability, carbon footprint. So everything that you really have to set up is the simulation setup. Other than this, it's pretty straightforward. So here, let's just keep for this part, the base setup. So I have one restraint and one surface load. So you can select directly surfaces in cognitive design using that select cut face block. So here I can just select the faces that I want to fix. So I can fix, for example, the 4 bottom holes like this. On the bottom here, I will select the faces where I want to put a load. Let's say the 2 holes on the top here. And then, because everything is already connected, I can just run topology optimization, so I can have a first version of my part. So here I just use the base parameters. So the ones that you really want to change, I would say, would be the volume fraction and the max iteration. These are the two most important ones. So this one is the target of weight that you want to have. So here we are aiming for a 50% weight reduction. Max iteration is like the maximum number of steps that you allow the optimization to do. So some people, they just put a really big number and then they stop when they feel the result is right. So you have a graph here where you can track the evolution of the weight, for example. And if you see that it becomes flat and that is stagnating, then you can stop. But otherwise, the software will do it for you. So here we can see little by little that it's reducing the weight, right, of the part. So all of this is using the meshless simulation engine that we integrated. So as you can see, it's quite quick. We can have in minutes a topology optimized part. And then if you play on resolution, or if you have like a really big part, like a turbojet engine, then it will maybe take 1 hour, right? But yeah, most of the parts, you would have them in a few minutes, 10 minutes max. So here we can see that we are already converging to a solution. So it's looking pretty good. I will just leave the calculation to run a little bit longer so it can kind of distribute the material in a little bit better way. You can see that it's still a bit moving the surface. So it only puts material where it's needed. So what it does in the background is it tries to aim for 50% weight reduction, but by having the highest stiffness, according to my load case. So that's why here it's still changing the surface, because it can see that it can have a higher stiffness by still optimizing the geometry a little bit more. And after this, what we can do is post-processing of that shape to make it fit to a specific process. So for example, here, right away on the right, I have it set up for die casting, but we will see together after that we can change the process and make like design parts for the processes. Let's keep die casting for now. So my part here is, yeah, looks like the optimization is finished. So I have something like this, which is the best material reduction for that specific load case. I can see that if I wanted to make this in die casting, here I have a little bit of undercuts. So maybe we want to fix this. So we can do this with that function here, manufacturing driven design. So fairly easy. For each process, you have a set of rules here that are basically the design rules for that specific process. So here, for example, we have the minimum thickness. So we can set up a value here. And if sometimes here it's not the case, but sometimes you can have thin sections on your optimized results. So you can say, okay, I want everything to be above 2 millimeters, so it will do the job for me. So here you can see I've checked undercut filling here. So it corrected here the undercuts that I had. So it made a straight surface. So instead of having a concavity here, it just corrected it and made it straight. And then once I'm happy with my part, I can just run the simulation to check whether I'm still meeting the requirements or not. So usually when you do a project, you have like a maximum stress that is tied to the material. You maybe have a stiffness target too, so some displacement value that you don't want to be above. So here, again, meshless simulation, so it's fairly quick. And I have the stress values for my part and the displacement. Can calculate also the other KPIs. So here we have manufacturability, cost, and carbon footprint. So I just let them run. Yeah, and for manufacturability, you can optionally go have a look at how it is. So for example, here, I can see that everything is green. So the thickness of 2 millimeters that I've set is validated, for example. Or I can look at the draft analysis, for example, and I can see, yeah, what's the core, what's the cavity, and what zones would I need to put some draft angles. You can do it in the software. Here I didn't do it because it can take a bit long. But you basically see the idea, right? And then I can just send this to the Design Explorer on the right. So here, if I just save it, then it will appear here in my list of design iterations. And here you see that I have all the KPIs. So I have the weight. This is the safety factor. So the maximum stress is 3 times lower than the yield strength of the material. I have the displacement also, etc., etc. So if I wanted to make this a bit more meaningful, I would need to compare it with something, right? So what we can do is just put the design space as a reference. So here I will just here I have my design space that I've imported. I can just rerun the KPI calculation on the design space directly, and we'll add it to the Design Explorer. So here first I do the simulation, and then I will run the manufacturability and cost analysis. And that will allow us to have a comparison point in the Design Explorer. So here, let's call this reference, like this. Let's just wait that everything is calculated. All right, then I can just send it. And here you will see that I have a new point in the graph and a new part here, reference. And here, what I can already do is I can set this, so pin this design to say, okay, this is my comparison point, and you will see how it changed. So we reduced the weight by half here, went 1.2 kilos to 600 grams, but the stress is a little bit higher. So before we had the safety factor of 4.4, now we have 3, which is still acceptable. Manufacturability is a bit higher, and the cost is lower also, which is nice. We reduce the cost by half. And everything is parametric, right? So if I wanted to do like a different iteration, I could just do it. So for example, let's say I want my part to be in machining. So I can just change machining here, right? And here you can see also some parameters that you can use for machining. So you can choose, for example, the axis where you want to machine. So here it's 3 axes. You can choose also, like as always, the minimum thickness. Minimum feature spacing is also nice. It's to remove small cavities. So if you have like a really thin pocket, it might be expensive to machine. So you can remove them. And so here I can just redo the calculation. And I will see my new parts for machining. And here you can see when we apply this for machining, it's way more prismatic. So here it's in 3-axis mode. So you really have it's a bit bulkier, but it has a lot of flat surfaces that would be cheaper to machine. And then I can just rerun these KPIs, right? I can rerun the simulation. And here I will just stop here to show you something. So like maybe one of the questions, I can't see them, but maybe one of them is how do you calculate the cost, how to calculate the carbon footprint, etc. So this, we do it through these, what we call macro blocks. So it's basically templates that you can use to store some values. So here it's a template for die casting. So obviously we might want to do the machine one in machining, right? So I have that CNC one here. And if we have a peak inside, you can see here all the values that are used for all the KPI analysis. So these ones, for example, are for cost calculation. So you can set up quantity, you can set up hourly rate. So for example, my machine here is 15 euros per hour. You can set up a material cost and also recurring and non-recurring costs. So recurring is for every part that you make. So it will be times 100. And non-recurring is for the whole batch. So with this, it's fairly easy to adapt it. For 3D printing, for example, you would put heat treatment as a non-recurring cost, but you can put sandblasting as a recurring cost, for example. Here also, I have some process settings. So for machining, you can set up the speed, the cutting speeds. And I have the same for CO2. So here, I can just connect everything to my machining template and reconnect it again here. Tac, tac, tac. And with this, my analysis will run for machining this time. So I do this, I do this, I do this. Okay, so I have new costs. And then I can just call this one, let's say 3. I've lost track of numbers. Machining. Save it. And here I have yet another iteration. And here, if we look at the KPIs, we can see that the machining one is still lighter, not as light as the die-casting one, but it's safer. So if, for example, you want to prioritize to have a lower stress, this one would be a good choice because we have 10 megapascal less here in the machining one. So that's the kind of study that you can make. You can do it through the graph too also, if you have a lot of parts. You can set up anything, like the safety factor, for example, and then you can see, okay, this part is the cheapest and has the lowest safety factor, for example. You can do it through filters also. Yeah, useful if you have many parts. When you do DOEs, for example, it becomes really handy to have these tools. Yeah, so really straightforward, and you can iterate on anything, right? So, for example, if I wanted a little bit different topology optimization result, I could say, okay, maybe let's target 40% weight reduction, and then I can just rerun the optimization and then add it to the Design Explorer. So you get the idea. But here, just in like I don't know, 15 minutes, I could already design, yeah, three parts. Yeah, and you can do way more, especially like soon we'll be adding that DOE feature. So you can just automate all of this. So you just say, okay, try 10 designs, and then I will choose which one is the best. So all of these things are possible. And here, really quick, I just change the volume fraction here. And then afterwards, if I wanted to add this to the Design Explorer, I would just need to recalculate everything. One of the first questions also is, can the changes propagate automatically? So in that case, you can just like recalculate the latest computes. So it will do everything for you in line. We don't calculate things automatically because operations like this, for example, are pretty long, right? So you don't want to run it automatically if you change a parameter, right? Yeah, and so you can see here that we'll have a different variation. That is, will here target a little bit lower weight, right? It's targeting 40%. So the part will be a bit thinner. Yeah. So fairly straightforward. And the beauty of this is here, until now, I've been iterating on the same part, right? So I've been running calculations only for that part. But usually what I can do is, okay, here I finished my project. It's really nice. Oh, yeah, by the way, you can export this as a report also. So I can just create a PDF out of this and then just go have a look at it. So here. So here you can see my report and all the results, like the filters that I've used and the KPIs are stored in that report. You can have it as a CSV also if you want to do some post-processing on it or feed it to an LLM, right? So it can make your report for you. Here you have the material properties. Yeah, and here you can see, okay, I have a little bit thinner version of my part. It's nice, I like it. So yeah, this one too, I can just send it to the Design Explorer, right? Just like connect it to simulation and then rerun everything again. So I can just stop it here. Okay, let's say this is nice. So I can just, let's say I bypass the the manufacturing given design step. I like it as it is. And then I can just rerun the simulation and then rerun these 3 KPIs. And then I will have my part. Yeah, then run these 3. Let's say I have a really good 5-axis machine, so I can make this in machining. And then, yeah, just I put it here, maybe 2, save. And here I have my new part. And again, I can see the difference. So this one is the lightest, of course, because I've set up a lower stress, lower weight constraint. But then you can see the drop in stress. I have a higher stress and a lower stiffness. Still, yeah, pretty good alternative. Yeah. And yeah, as I was saying before, if you want to do this for a different part, really simple. I can just go back to the beginning, import a different part. Let's take that one. So another bracket. So what most people do is they create workflow per family of parts. So this one is fairly nice for brackets. You could have like different workflows. If you have like really thin parts where you can't really do topology optimization, then you can use some simulation-driven design to optimize the thickness of your part, and that can also be saved as a template. And here, yeah, let's change stuff a bit. So usually you don't always use the same simulation setup, right? So of course I need to reselect the surfaces. So let's put a load on the 3 surfaces around. But yeah, okay, let's say this time it's not a force, it's a torque, for example. I can just set up the torque here. Let's say it's in the Z direction, and the value is 100 Newton meters, for example. All right. You can add more loads also. Here, you just need to connect them to the load cases. You can do several load cases also. Yeah, and here I can just rerun the topology optimization. So, okay, yeah, let's target 50% rate reduction. Then I can just run it again. I don't need to connect everything back, right? Everything is already set up, so I can just start from my past project, and it will do the calculation. So here it will run again. I will then have my optimization for this part. And yeah, let's spice stuff a bit. Let's say maybe I want this for, I don't know, forging. I can just leave the calculation be. So here also in the optimization, you can set up some thicknesses to protect. So here maybe it's a little bit too big, so I can change it here. So where you apply some loads and some forces, you can set up a boundary thickness here, and it will keep, before it was 5 millimeters, so you can see here that it kept 5 millimeters around the holes. Here I set it to 1, so I will have a thinner interface around that part. These kind of things you can also do in post-process. So what I would advise is try to have the best theoretical part in topology optimization, and then during the post-process, you can add back material. Usually, you have like fixed thicknesses for machining, right? For example, that you want to keep. So yeah, you can do this as post-process in using Boolean operations, or we have also some blocks that can do both like smoothing and putting back these regions on the part. Yeah. And here you will see it's optimizing little by little. And here I just reduced this on purpose to show you the thickness correction. So here you have a rather like thin zone, right? So using that MDD block here, you will see after that I will be able to correct this in order to fit to the process parameter. So here, for example, if I say I want 2 millimeters, then it will bring back 1 extra millimeter here. So just wait a little bit that it finishes. And then we can just run the manufacturing driven design. Yeah, and while it's calculating, I can show you a bit the tabs on the left. So here you have all your import and conversion tools. So what we call FREP is the implicit model, it's function representation. DREP is CAD models, and mesh are like surface meshes like STLs. Yeah, here you have some selection tools to select CAD faces, to select points. etc. You can move your part. You can also extract cylinders. This is pretty useful. If you don't want to select things manually, you can just get them automatically. Here we have the generative design tab, where we have like the methods that we have. So today I've showed you topology optimization, but we have two others, topology weaving and topological enclosure, that are used for different use cases. These are more like direct generative design approaches, which are still pretty nice. Here you have all the simulation stuff. So for simulation, today I've showed you mechanical, but you can also do thermal and thermomechanical. You can combine them. Yeah, and here the optimize tab, where you have like manufacturing driven design and also like simulation driven design, where you can tweak the parts using the simulation results. So here the calculation is finished, so I can just run manufacturing driven design here for forging, and then it will post-process my part. Here's, honestly, it's already pretty good, but at least it will correct this thickness here, and maybe add a bit more smoother. Yeah, that is also smoother angles. So that stuff you can do also. Here it's set up to 7, so where you have like sharp corners like this, you can smoothen them using that minimum spacing here, feature spacing here, which is pretty useful actually. If I make it a lot higher, then I will have a more convex part, which sometimes can be pretty useful. Yeah, and then I've showed you already quite a lot of times, so I won't show it to you again. But you can run the simulation and send this to the expert to iterate. Yeah, so that's everything from my side. I believe there might be some questions.
Yes, indeed. Actually, quite a lot of questions. So maybe what we can do is to go through them one by one and just make sure that we have answered them like correctly.
Yeah.
I think there was the questions on manufacturing-driven design and how does it work.
Yeah. So how it works is, so basically what you were seeing just before with the manufacturing analysis, where we detect some zones in color that might be too thin, for example, it's using these values. So for example, and each rule is something that we modify. So for example, thickness, it will look locally at the thickness of the part and add some material where we need it. So here you could see that before it was 1 millimeter, but here it went back to like 2 millimeters. So it's this kind of operation directly using implicit modeling. And it, like, the operations depend on the process. So for forging or for die casting, you want to remove undercuts. So we look at zones that might have undercuts and fill them, project them. For additive manufacturing also, we have quite a lot of corrections that we can do. For example, if you have holes in overhang, you can change them to diamond to have no supports. You can put some ribbing. Yeah, quite a lot of things that you can do. But under the hood, it's using implicit modeling operations. And so it's not using process simulation. It's really looking at the geometry of the part and making sure that it follows the geometrical rules of the process, the design rules. Yeah. And yeah, for manufacturing design, so yeah, as Vincent said, mostly rule-based, but you can save everything as a macro block here. So you can make your own little database in order to reuse it later.
Yeah, we are looking to add like more processes, but so far we have those 5, and we want to add as many as possible to cover more manufacturing methods. Mm-hmm. There was another questions on having other load cases, or more than one. And yes, effectively, you can plug and add new load cases that are different. You can add mechanical or thermal stresses. And we have another module that helps you upload, let's say, hundreds of load cases when you have very heavy stressed parts.
Mm-hmm. Yeah. Exactly, yeah. And yeah, because most of the project that we do, of course, like we have like 20 or 30 load cases. So you can set up inside the software. We will soon add also the capability in around September to import an Excel file. So if you don't want to set up the load cases in the software, you will be able to just import your Excel in the right format and then do it. Yeah, and yeah, nice question from Didier. So yeah, you can also start from just functional zones. So there are several ways you can go around this. So you can create basically a design space with the functional regions using an operation that we call shrink wrap. So let's try this on that part maybe really quickly so you can have an idea. So, all right. It's not a case that we encounter often, so we don't have a template for this, but definitely might be interesting to add a template for this. So how you will typically do is either you select you import your CAD regions like this, or you select them in the software. Then you can thicken it. But let me just make some space. All right. Yeah, so you can thicken them. So let's say, for example, I want to keep maybe 3 millimeters around them, like this. Okay, so I have a thickened version of my interfaces. And then you can use that shrink wrap function. So this one, basically, it will try to connect all of these together and try to make a volume around them. So usually you need to, so you have tools to measure inside the software. Here I have around 20 millimeters. So I guess if I use a value of like 50, I should be safe enough. And then you will see the results here. I will just put coarse so it's a bit quicker. So it will create a volume around all of these. So you can have a rough shape, like a rough design space of your part. And then what you would do from there is, so you can create non-design regions inside the software, or you can just import them from CAD, right? So I could just import non-design regions to open back the holes. But here you see, I've just started from the functional interfaces. I didn't use the design space. I can have a nice starting point. It's really nice to do some fast prototyping, actually. Yeah. So I hope this answers to your question. Question from Marco. Is there manufacturing optimization for different additive manufacturing technologies? So yes. So the approach that we have is like globally, what are the rules of the FAM? And then you just adapt them depending on your machine, basically. So for example, yeah, I can have like aluminum or titanium additive manufacturing, and then it's basically just and it's powder bed, right? It's just the values that you put in there that would change. So you would put like values for FDM or value for LPBF. So for these processes, for example, the minimum thickness can change, the overhang angle can change. We also check for like slice area variation if you don't want like abrupt changes. So all of these you just set them according to your process.
Yeah, we also have like I would say sets in manufacturing driven design that are specific to certain manufacturing process in AM. For example, depowdering. We have a way to depowder pass. It's something that you will not have for example, like FFF or filament-based 3D printing.
Yeah, two questions from Yves. So yeah, simulation right now it's only linear static, but so usually like what most of our customers do is they do quick iteration inside the tool because as you saw it's really quick. I can just make a design in minutes, and then at the end we just export it either as a step model, so we can reconstruct also the part as a step model, or as a mesh, FEA mesh. So for this we use a partner. And then like people just run the final validation in Abacus or in ANSYS. But at least most of the time that you spend like trying different designs, You don't lose them. If you had to do like one ANSYS or one Abacus validation for each of these, it would take weeks, especially if it's not like the same department. You need to send it to your colleague and then wait that the answer comes back. It's pretty long. So here you just like explore the design, say, okay, I want this one, and then this one I can just send it to simulation. And yeah, to be trained on the tool, yeah, as Vincent said, 1 or 2 days enough. For topology optimization, maybe some of you might already know how to do it from what I've showed, right? It's fairly easy actually if you use the template. Yeah, so as Vincent said, CFD is planned, yeah, using also our meshing partner VoxShell. Yeah, for the, yeah, so nice question from Didier. So we do, I would say, so topology optimization until now, it did only 40% of the work. You had like a rough shape and you can't reuse it as it is. Now with cognitive design, we do 80% of the work. So at least you have a part that is pretty close to the final one. However, like the final steps, like making the drawing, putting the tolerances, etc., we leave it to the CAD players. So you just export your part and then do the like the detailed design, right? The final like fine tuning onto your CAD platform. So we really like place ourselves in the advanced concept phase. Yeah. Yeah, and yeah, other questions. So yeah, all the calculations are on the PC. Nothing goes to the cloud. The software is fully on-premise. We don't even send logs. So yeah, you can use it safely offline. And yeah, right now I'm using a laptop. It's just a gaming laptop with 32 gigabytes of RAM. And you can see that it's already enough to do this kind of topology optimizations. If you have like really, really big parts, like let's say 1 or 2 meters, then we will advise to have at least 64 or 128 gigabytes of RAM. So like the software doesn't freeze while it's calculating. But it's pretty efficient, so that's why we do everything on-premise.
Yeah. Is there any other questions that you want to ask in the chat or live?
Yeah, I guess one last question from Marco. So how do we output? So yeah, I didn't show it, but we can export a part as a brep. So it takes a few minutes, so I won't be able to show it right now, but I can just show you one that is already calculated. And so the brep export that we have is hybrid in the sense that, so yeah, so here is a mesh, for example, and let's say I want to export this as a brep. As you can see here, it's a mesh with triangles. So you have that block here, advanced mesh to brep, that we can use to convert that part to a CAD model. And how it works currently is all the zones that touches the design space will stay clean. So here you see I have clean cylinders, I have clean planes around the part, and all the optimized zones are patches, organic patches like this, so NURBS patches. And this is already really nice because what you get in most other generative design softwares is a fully organic part. So everything is patches, and for example, if you wanted to do simulation on it, you wouldn't be able to select these cylinders. So that's what the conversion method that we have now. Yeah, so yeah, that's what you get. So you can easily still edit this, add some over thicknesses, for example. Yeah. I would say for diecasting, maybe there is still a little bit way to go as for drafting, right? Might be a bit tricky to put drafts on a part like this. So at the end of the day, maybe you need to like redesign it. But yeah, already we've done some projects like in machining, for example, in 5-axis, where we're able to use these geometries. It's something that we could put quite a lot of effort on, these like mesh to brep stuff, reverse engineering stuff, basically. So soon in the next version, you will also have a version for machining where it truly gives you like true straight faces, which will be already more usable.
I think there's another question. Can this functionality be used for reverse engineering?
Yes. Yeah, actually, it's the same concept. So you can use this for reverse engineering, yeah. if you do it from a scan, we also have some tools to try to, if you have some holes in there, to correct them. So yeah, you can use that. Thank you.
Is there any other questions? Well, I guess we'll end it here. Thank you so much, everyone, for joining this webinar. We'll share the replay very soon. And if you have any question, feel free to ask us directly by sending us an email or contacting us on our websites.
All right. Thank you, everybody.
Thank you.
Have a nice day.
Have a nice day. Bye-bye.